So today we're excited to have my good friend Yannis Kevrekidis from Johns Hopkins University to come and visit us. The planning was to come last spring, but we had a storm here and there, if I remember, and so half the way things were interrupted.
It's a good thing I didn't fly to Chicago because the next flight was cancelled, and you told me they will cancel it.
Yep. So, Yannis, graduated from the National Technical University of Athens, like most of the good Greeks, like myself. He studied in Minnesota, where I was myself spent some time there. He was at Princeton for
31 years.
31?
Yeah.
All right. Okay, not counting, 31 years. And he recently, 2 years ago or so, moved to Johns Hopkins to join the Bloomberg Corporation, right? And so today he will speak and entertain us on no equations, no variables, no parameters. Even, I was actually pointed that the word even was added to the slide. It's a revision from the previous slide, right? Yes.
Right. At some point I sent this title to a seminar, and then there was an ice storm and I missed it. And then they also wrote, and no Yannis. But as Nick said, there's people in blue that are from Hopkins and people in orange that are still people that started with me in Princeton. And I should also say that last time that I was here, a long time ago, chemical engineering was still in the same building and Schmitz was around and so on and so forth. So it's been quite some time that I have not been here. So I had three things to tell you, and I kind of realized as we're coming that three is probably too many, so I will jump over one of them and tell you about two things. I hope I will be a little entertaining. This is a strange title, so I mean something. I hope I will be able to explain. I stole this slide from Julio Pino, who is your neighbor. He is Dean of Engineering at Northwestern. He says there is simple systems, a few degrees of freedom, complicated systems, many degrees of freedom, but each one of them is designed to do a particular job. And then complex systems, many degrees of freedom, but many fishes, many people, many molecules, but they are in some sense interchangeable, and whatever interesting happens because of their interaction. He wrote this slide because he wanted to contrast complicated and complex. I stole the slide because I wanted to tell you that a billiard ball is simple if you think of it as a billiard ball, but it is extremely complicated if you think of it as the molecules that comprise the billiard ball. So what I'm trying to tell you is that whether something is simple or not depends very much on the eye of the modeler, on whether the modeler can usefully model it at a simple level or at the complex level. Almost everything we do is complex. When we can coarse grain them, we can usefully think of them as simple. But they are all complex, I think. So this is my standard kind of little example of something that we started doing a long time ago and we called equation free. It's a model of plankton dynamics that comes from a good friend, Tony Roberts, who is a mathematician in Australia. He wrote a paper about it in 2001. And what I want to show you is two versions of the same movie. Let me stop it and tell you what you see. Here you see a whole bunch of dots. Each dot is supposed to be an agent in an agent-based model of plankton. These little dots, what they do is that they do random walks, they give birth, they die, and then they're also swished around by currents in the ocean. This is a terrible mess. This is the right macroscopic quantity for this problem. It is the pair correlation function, which basically tells you how many neighbors you have on average as a function of the size of the neighborhood. How do I know that that's the right macroscopic variable? Because of Tony Roberts' paper. The thing that is important is I want you to look at the same problem observed at this level and at this level. You've already seen some of the movie. Let me play the rest of the movie, and what you will see is that on this side you have things that I keep running around. There's striations. It is horribly complicated. Here what you get is something that looks like a partial differential equation which with a lot of little noise went to a steady state. So again, this is in the point that the problem may be simple or complex depending on the level at which we are usefully observing it. And what we did a long time ago, this is the equation-free stuff, is this idea of I have a problem for which I have particles, let's say agents, but I do not know the right partial differential equation for the macroscopic quantity. So this is a problem that I trust in my heart that I can coarse grain, but I don't know how to write the coarse grained equation. At least I know what's the right coarse grained quantity. The idea is that if I, let's say, want to integrate the equation, for a given initial condition, I need the time derivative. But I don't have a macroscopic equation to give me the time derivative. So what do? I take the initial condition at the macro space, pair correlation function, create particles that have this pair correlation function, run the particles for a short time. So I do a computational experiment. I use the microscopic simulator as a computational experiment that I design and run in short bursts as necessary. I observe the evolution of the particles by looking at the pair correlation function, and then after a short healing time, I estimate the time derivative of the pair correlation function. So I am then doing an Euler step. I am still doing the same thing that I would have done if I had an equation, only the macro time derivative that I need to do this step does not come from an explicit formula, it comes from short bursts of microscopic simulations. So if you think about it, it's not fair to call it equation-free. There are equations, but at the particle level. It is at the macro level that I don't have explicit closed equations. And so the idea is that if you have in your pocket the micro code, you can design intelligent short bursts of computational experiments with the microcode to get exactly the macro quantities that you need to do scientific computing with. Okay? What is there's all kinds of questions, of course, how long do you have to run and how big the step has to be and so on and so forth, and I'm not touching on this at the moment. There are reasonable answers to a lot of this. As a matter of fact, I have a slide that says that you can take, so this we call this with Bill Gear, coarse projective integration. It's coarse because we jump the macro quantities, it's projective because we project forward in time. And the basic idea is you use the micro to come down to a slow manifold, and then you estimate things on the slow manifold and jump, run again the micro and jump, and so on and so forth. Again, what's the idea? The idea is if you know that there exists a macro equation, and you know what the right quantity is in this macro equation, then you can use the idea that this equation exists to run the particle code smarter. And so this is, again, the main point. You have a detailed simulator. Somebody tells you what is the right good coarse variable. You don't have the macro equation, but you can use the idea that the coarse equation exists to accelerate the simulation. You don't run the particles in all space and all time, but little chunks of space, little chunks of time, and you can fill in the rest. So we call this equation free, but again, the most important thing is to do this, somebody, and in this case Tony Roberts for me, has to tell you what is the right macroscopic quantity in terms of which you can describe the system. So it's kind of interesting to think about this. Where do good macroscopic quantities come from? Where do good coarse variables come from? Like we kind of all know, we do chemical kinetics, we use concentrations and temperature. We do continuum mechanics, we use deformations and stresses. So all our textbooks are written in terms of cases where we know what the right macroscopic variables are. Well, what if you're working with a new problem in which you have no idea what the right reaction coordinate, the right coarse variables are? And this is the place where what we do, one thing is if you work, let's say, with distributions, you keep enough moments, you will do a good job. Or if you have worked for a long time with a system, maybe from experience you have a good idea what are the right variables. Sometimes I'm thinking, I try to think of a good example for this. You may have maybe in your company you have a friend that when, let's say, I hope it's not politically incorrect, when they see a new couple, they observe them for a couple of days, and then they say, this couple will stay together for a long time, they fit. Or they can say, nah, these guys, they're not going to last. In 2 weeks, they will kind of. So these guys have a good idea of the prediction. But if you ask them, can you tell me exactly what is it that you saw that does this? Maybe they know and they can tell you, or maybe they don't know. My other example is we give our money, our retirement money to funds. And we kind of hope that the people that will run the funds have a good idea about predicting the market. But you could ask them, do they exactly know what they observe, or is it half things that they know and half things that they their brain has done the data mining and knows. This has to do with what you told me about control based on inputs and reflexes. So what I'm trying to say is there's cases where with a lot of work you can get from the Boltzmann equation the Navier-Stokes. And there's cases where somebody just knows what the prediction is without maybe even knowing what the right variables are. The important thing, and that's the main thing of the discussion today, is that what we can do these days is that we can look at the data and we can use machine learning to figure out what might be good macroscopic variables for describing something. And this is not a big deal at some level. You all, I think it's 120 years, 130 years that people have been doing principal components. You get very high dimensional data, three-dimensional, where every point needs three numbers to describe it. But if the data live on a hyperplane, then you can find the right vectors, and then you can boil it down to very few, 2. So in this case, the important thing is not really the reduction from 3 to 2, but that doing data mining, in this case singular value decomposition of this data, gives you new coordinates in which coordinates the thing is lower dimensional. And let me say that if this was chemical data and this was like carbon, oxygen, and hydrogen, this is 0.7 carbon minus 0.3 hydrogen, and that's not a very good variable for chemistry. It is a very good variable for representing the data parsimoniously, but not necessarily a good variable to think chemically in. So so this is, if you want, one of the main ideas, the no variables part. We're going to do data mining, not linear, but non-linear data mining in order to get good variables. And I thought that I was going to tell you an old story. So this is early 90s, and we were trying to get data from experimental, and we were trying to get models from experimental time series. And so I want to tell you a little bit about how one was getting good coarse variables back then. What you see here is time series from electrochemical experiments. This is copper electrodissolution at different potentials. And so here you see the behavior is steady, the dissolution current is steady in time, and then it becomes periodic, and then messier periodic. Actually, this is a period 1, so there's a Hopf bifurcation, and this is a period 2, and then you get a period 4, and then you get chaotic behavior. And what we were doing was this is the old shallow as opposed to new deep neural networks. In 1988, people used this kind of neural network where you use, remember we only measured one thing, so we used time delays of the one thing in order to predict the next. So this is very much in the spirit of NARMA models. You use history in one variable to predict its next value. But it turned out that when we did this, we had a continuous system that we tried to model by a discrete system. And you might think that that's okay. Well, it actually turns out that while the short-term prediction can be quite accurate, if you look at the long-term prediction, the attractors of the discrete problem, they look very, very, very qualitatively different from the continuous ones. Take my word for this. If you have a continuous system that has a limit cycle, if you train a discrete problem to it, there's a good chance that there is resonances and frequency lockings. So it is qualitatively wrong to use a discrete model in order to learn a continuous dynamical system. So what we did, and we were kind of happy with ourselves back then, this is 1992, is to say, well, we do have discrete data, so we have data at some moment in time, and data at a later moment in time. We want a neural network, but we don't want it to be like a NARMA model. Let us think of the following thing. If we had a Runge-Kutta, so pick your favorite numerical algorithm. This is like a fourth order Runge-Kutta. If you thought of a fourth order Runge-Kutta, what does a Runge-Kutta do? It takes the data at the beginning and calculates f of the data. And then it takes the data and perturbs it a little bit in the direction of this result and calculates f of this. And then takes the data and perturbs it a little bit in the direction of this result. You do this 4 times, and then the result is a linear combination of these 4 iterations. So what we did is that we created a recurrent neural network templated on the Runge-Kutta. We took the result, we then through the neural network, we get K1. We took K1 and perturbed it by h over 2 and added it, did it again and again. And by showing discrete data, we were able to learn a network that gave us the right-hand side, not the time one map, but the right-hand side. If you do this, then you get, look, you get the correct attractors, you get period doublings, and you can also find bifurcation diagrams, which is what we were interested in. And the question is, to have chaotic behavior, you need several variables. So what are the variables in terms of which we learned these differential equations? Well, the variables came from an autoencoder, which at the time they were called bottleneck neural networks, or they were called nonlinear principal components. So you take a window and then you get that 20 delays can be summarized. If you take a network like that and you teach it the identity, this means you take 20 numbers and summarize them as 3, and then from these 3 you can reconstruct the 20. Why am I telling this to you? I'm telling this to you for historical reasons. We did this, we did a good job with this. We created very nice reduced models for turbine instabilities for United Technologies and so on and so forth, but we couldn't write any papers because this is a nonlinear, non-convex optimization problem. If it works, great. If it doesn't work, you don't know if it doesn't work because the problem is not reducible, because your initial conditions were bad, because your code has a bug. You understand? There is no theory for this. So I always felt that this problem of getting effective reduced data through autoencoders is in some sense a hopeless problem, not a problem that is solvable, but a problem that you play with. It's like finding Lyapunov functions. Either you can find one or you cannot. If you cannot, it doesn't mean it doesn't exist. And then what happens, so this is 1992, and then what happens is 2000 comes, and in 2000 there's 2 back-to-back papers in Science magazine, and one of them is called isomap, and the other is called local linear embedding. And if you don't know about them, at least take this from this talk, Google isomap. What people do is that they took data that are high-dimensional, 3-dimensional, but look now, they don't live on a hyperplane, they live on a nonlinear manifold, and then what they were able to do is that they were able to create coordinates phi 2, phi 3 that unroll this manifold and parameterize it. So the idea is that you can now find parametrizations of data not only that live on hyperplanes, but that live on nonlinear curved manifolds. And why again am I showing this to you? Because these guys are good reduced coordinates in terms of which to describe the data. If you have dynamics on this Swiss roll, then these are 3-dimensional dynamics, which however can be summarized as 2-dimensional dynamics. So one of the simple dumb things to tell you from, maybe again to remember, is that machine learning, and in particular data mining, and isomap is one version of this, but diffusion maps, which happens to do with what we do with Rafi Koifman, is another such algorithm. Again, you might want to Google diffusion maps. Is something that will take the data, process it, and give you good reduced coordinates that describe the data. So if I have a messy problem in which I have 100 variables, but maybe only 3 combinations matter, there is systematic ways, I'm oversimplifying, but it is not completely wrong to say, there is good systematic ways of finding out from the data what are good 3 coordinates. What's the bad thing about this? Same thing as for principal components. In the same way that 0.7 hydrogen minus 0.2 nitrogen is not a good chemical variable, these variables are wonderful variables to represent the data and compute with, but they don't necessarily have a nice physical explanation. Is that a problem? If you want to compute, maybe not. If you have time and if you like it and remember, ask me at the end about explainability. There is something that I can tell you about physical interpretation, but the basic idea is you do this, you get wonderful sets of reduced coordinates, they don't make physical sense. Do you mind? Like, if you take logarithms and add them instead of multiplying the numbers, do you mind that they are logarithms? As long as you can translate back and forth, maybe you don't mind. Okay, we can come back to this. So here is a little ridiculous example of doing this. This is a 2-dimensional function that I want to maximize. You can kind of see that most of the function lives along a 1-dimensional ridge. And if I knew this, then I could do 1-dimensional optimization rather than a 2D optimization. So what do? You can think of this as a little bit of projective integration. We have a local optimizer, which in this case happens to be something ugly like simulated annealing. We run the simulated annealing, it very quickly goes to the ridge and then jiggles around on the ridge. if we continued it, we would eventually get there. But if we don't continue it, that's the idea that I want to say, we take this data and we process the data and we see that the dynamics of the algorithm itself are one-dimensional. Then, by processing these data, we can get a coordinate along which the dynamics of the algorithm move, and then we can make a big jump. New short burst of local simulated annealing, new data mining, new jump. New short burst and new jump. In the time that it takes to get up there, again, this is just a caricature to make the point, if you had continued the simulated annealing, it would only have explored up to here. So the basic idea is, it's an interesting idea. Think of your algorithm itself as an experiment. You have a traditional algorithm. You can process the dynamics of the algorithm and figure out if it is maybe lower dimensional, and you can use that to, in principle, accelerate the algorithm. And so one of the things that we do, and I am going to jump over this, is that let me just kind of say the outline for this, is that if we have something that lives in a potential, we can look at the data from the simulation, and if the data very quickly come to a lower dimensional manifold, we can use the data on this manifold and try to push the data, bias the initial conditions, so that we go up a potential well. And so what we have done, and there is a PNAS from this in 2017, is that we have used this to look at things like protein folding. The idea there is that you may have a useful low dimensional problem, so maybe there exists a reaction coordinate that is low dimensional, but this reaction coordinate is some unknown function of the positions of all the molecules, so you don't know where it is. If you run molecular dynamics for a short time, you can figure out that there exists an effective one-dimensional local manifold. And then you can go to the edge of how much of this manifold you have sampled, estimate its derivative, and then create a smart initial condition that is further away up the effective free energy. Run it again, collect the new data, again, same idea, but I'm telling it to you again and again. You get the data from the molecular dynamics, you realize it's low dimensional, and then you can use that in order to create a new biased initial conditions. You do it enough times, and with a little luck, if indeed the problem does reduce to a lower dimensional manifold, you can get something to escape a free energy minimum. Let me jump over this example, which is how to do calculations with on-the-fly reduction for molecular dynamics simulation. And since I have at least two control friends here, Professor Antsaklis and Professor Cantor, let me give you a problem that has more to do with controllability and observability. So this is, for those of you that play with dynamical systems, this is a two-dimensional set of nonlinear differential equations that depends on two parameters. And this is the bifurcation diagram in terms of the two parameters. This problem is a representative of all problems in the world where two things go wrong at the same time and nothing else. Like you're driving the car and your tire explodes and the radiator also explodes at the same time. All problems in the world that have only two of these defining conditions and nothing else wrong can be mapped close to that critical parameter value to this set of differential equations. It's called Takens-Bogdanov because of the people that have studied it in dynamical systems. This for me is just an example. I don't want you to worry about this. I just want you to say, here is a general, this is a representative of a general dynamical system that has some variables x, some evolution equations f, some parameters p, and some observation function g of x, and I really know nothing of this. All I have is that I have different experiments at various parameters. I don't know at what values. I just have experiment number 1, experiment number 2, experiment number 3. I measure time series, but I don't really know what it is that I measure. I just measure time series that come from the problem. And what I'm going to try and do is that I am going to create a realization of the problem, a realization of its state variables, a realization of its parameters, even though I have, maybe this is what I should say, I have lots and lots of data. It's just that I don't exactly know what the parameter values are, and I also don't know what it is that I am measuring. I'm only guaranteeing to you that you're measuring functions of the state of the system. You don't know what functions. So this is Kalman, who died a few years ago, And this is a guy who did something wonderful in 1981. You can tell it's 1981 because of his hair. And I don't think that he did many things after that, right? I mean, B.C. Moore, I don't know, Pano, if you remember it. He
was very visible for a while.
Yes, and then somehow, anyway, so what he did is that he used singular value decomposition in order to create minimal realizations of linear dynamical systems, okay? And here is the idea, but now for a nonlinear dynamical system. Let's say that this is my two-parameter space, but I don't know what my two parameters are. I have a blind monkey who turns a knob, and by turning a knob, throws a dart somewhere in parameter space. And then at these conditions, at blue conditions, what I do is that I go and measure a whole bunch of short transients from the dynamical system. I don't necessarily measure the state variables. I measure functions of the state variables for a whole bunch of different initial conditions. And then there is another dart at red conditions, and then I get red hairs, if you think of them as a lot of little hairs, and then at the green conditions, and I get, and so if you think about it, what I have is a whole bunch of experiments, and for each one of these experiments, for every trial, if you want, I have a whole bunch of measurements. But as I said, I don't know what the parameter values are. I just have a label, experiment 19. And I don't know exactly what function of the state variables I am measuring. So if you think about it, let's say you have 50 experiments and 1,000 initial conditions for each experiment, you have 50,000 hairs. And you really have no idea who goes with whom. You just know that blue goes with blue, but you don't know what it is. And red goes with red, and you don't even really know the colors. You just know these 1,000 hairs belong to experiment 19, and those 1,000 hairs belong to experiment 3. So the point is, how do you make sense of this? Let me see if I can do a good job. This is also a PNAS in 2017. So what you do is that you take all the hairs that you have measured, okay? And what you do is that you analyze these hairs, think of each one of them as a long vector, as a data point. So you take these 50,000 data points and you analyze them, and let's say that you find that it's a two-parameter family of hairs, parameterized by, let's say, are they more to the left and more to the right, versus they are straight or curvy. If you look at which experiment the hairs come from when you do this, then, well, they come from all over the place. Let me try and explain this. Suppose that each experiment, like I'm traveling across Europe, and in each experiment I visit one city and I pick 1,000 people from that city. Then you could say, these are the people that I picked up in Stockholm, these are the people that I picked up in Athens. You see that in Stockholm there is a lot of long blue straight hairs. Let's say that these are tall blonde people. So in Stockholm, there is lots of tall blonde people, but there are some tall blonde people also red in Athens, and there are some tall blonde people with purple in, I don't know, in Barcelona. If you go to Athens, you're going to find lots and lots of people that have short curly hair, but there will also be some people, like these blue ones over here, that have short curly hair in Stockholm. The point is, if you analyze the data without caring from which experiment they come, then you get a good space in which to embed the data, but not a good space to embed the experiments. Okay, here is the fun part. Now that we have a good idea of how to compare different data, what we do is that we take all the people from Stockholm and all the people from Athens, and what we do is that we compute an earth mover distance between the Athens people and the Stockholm people. That is, we try to find among permutations the minimum distance between the one ensemble and the other ensemble. And now, because we know how to compare individual people and we know how to compare ensembles of individual people, we can kind of get a sense of how different the people in Stockholm are from the people in Athens. So now, if we're going to take a blonde person, a tall blonde person, now, and compare it to somebody else, we can compare them as far as their characteristics go, but also now we have an extra number that tells us this tall blonde person is from experiment 29 and that person is from experiment 13, and we have a distance between experiment 29 and experiment 13. Please consider it by doing a first analysis based on only the features and then looking at the ensemble of data in one particular experiment. We got a first estimate of how far the two experiments are. So when now we're going to compare people, we not only compare how close the people are, but how close the people are in terms of features and how close their corresponding experiments are from. So now when we compare people, we also know something about how close the corresponding experiments are. And this corresponds a little bit like giving a little color to the hair. Not only do you know what they look like, but you have a sense of how different their experiment is from another experiment. And then what we do is that we iterate. We look at the people and then use the people to take distances between experiments. And then we look at the people again, informed by our first estimate of the experiments, we get a new distance between the experiments. We look again at the people with the improved distance between the experiments, we get a third iterate. And by doing this a couple of times, you actually can figure out that there is a two-parameter family of trials, and you can actually reconstruct this two-parameter space. And the way that this happens is that this is the original two-dimensional parameter space. You remember there was a critical point somewhere here. There were different behaviors in the different colors. What we did is that we took 400 time series from each one of these conditions. We mixed them all up. We did the data mining that I told you. I didn't perfectly explain, but I hope I gave you a little bit of a sense. And then one day, what happens is that Ronen Talmon, who is now a WB professor at the Technion in Israel, comes back and says, you know, if you take these data and mix them up so you don't know how they are, you do the data analysis, and the data analysis will come and tell you, you know, there is these guys are a two-parameter family of data. They should be organized topologically like this. What does it mean topologically like this? That the nearest neighbor of this experiment is this, 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 and this. So it will take this mix-up of completely agnostic presented experiments, and it is going to create a realization. First, it's going to tell you it's two parameters, and then it will create a realization of the parameter space. Furthermore, it is going to tell you that it is two variables, and it will give you a realization of the state space. If you remember, the state space was a square, xy. I hope your eyes tell you that what you get out of the data mining is a rotation and slight deformation of the square. So you get something which is homeomorphic to the original space. You don't get exactly the original space. You have no way of expecting you will get it. But you do figure out that there's two variables, and you get something which is one-to-one with the true two variables. And what is the big thing? The big thing is what is said here. Before, if I took a hair out of all of this sack, this would be something, I didn't know what the parameter values were, I didn't know what the variables were. Now, if I pick up a hair, I know what the effective parameters are. They are the things that come from ordering the trials. I know what the effective variables are. They are ones that come from data mining the initial conditions. And then I also know what DDT is along the trials. That is, now I have a realization of the parameters, I have a realization of the state variables, and I have a time derivative. So if you think about it, I have a tabulated model in terms of a minimal number of parameters and variables that is one-to-one with the truth. What is the tools that have been used in this story? All that has been used in this story is smoothness. What initial conditions give you trajectories that are close to other initial conditions? For what parameter values do I get for the same initial conditions nearby trajectory? So it is only smoothness that goes into being able to construct this minimal, we kind of happen to know that it is minimal, that it is a diffeomorphism we can kind of see with our eyes and we can test numerically. So what is the point of this? This is something that Ronen included in the paper, and I think it was very qualitative but kind of interesting to see. So if at the end of the day today you went home, you can say, oh, this guy showed a movie in which there were two coupled pendula. Oops, wait a minute. and these two couple pendula were oscillating. And then, one can analyze the motion of pendula and find their normal modes. Here is a situation in which the pendula are oscillating, but the spring between them becomes stiffer and stiffer, so the oscillation becomes faster and faster, right? So this is something that it is very easy to explain to somebody else in a few words. A pendulum, two pendula coupled together with the spring gets stiffer and stiffer, the oscillations become faster and faster. Here is the same movie observed in kind of a funny way. What you do is that you break it in 10 by 10 pixels, and then you randomly rearrange the pixels, then you average the color in the pixels, and then you multiply them with a random number. So this, you kind of have to trust me, is a simple invertible transformation of the actual movie. And if I play this one, maybe your eyes will tell, can you kind of maybe see that the oscillations become faster and faster? But okay, you have to trust me that it is the same movie. My point is, this is exactly the same information as before, exactly the same frequency content as before. You can create the same model from this like before, or models that are mappable to each other. The point is that this does not have an obvious physical explanation. So what I'm kind of trying to say is that there is different representations of exactly the same thing. You can use the bad model, the one that is difficult to explain, in order to make predictions, but you don't have the physical understanding of why the predictions are correct. So there is versions of the model that are understandable and we are confident about them, and there's versions of the model that are completely data-driven. In this case, I happen to know how the one-to-one transformation is, but you can make exactly the same predictions based on models that come from the messy data. It looks a little bit like looking into a crystal ball. You ask a question, you get an answer, but you kind of don't really know the mechanistic explanation of why it is that you get an answer. So this is, that's why there is a question mark up there. There is science in the algorithms, but you don't have physical understanding. And this is again the same thing that I told you before. There is this issue. You can be predictive, but your variables don't necessarily make sense physically, or your equations don't necessarily make sense physically. Okay, so I've told you about no equations and no variables and no parameters in these examples. Now I want to say no space and no time. I don't know how many of you saw the movie Argo. You may know that in 1979, when the Americans left the embassy in Tehran, what they did is that they shredded the secret documents because they didn't have time to burn them. And then Wikipedia says that the Iranians put a number of skilled carpet weavers in the room and said you can't get out unless you put the documents back together again, and they actually did it. And so here is a partial differential equation, it's a Ginzburg-Landau, one-dimensional space and time. This is the behavior of one of the fields for it. I would like you to think that you solve the partial differential equation, and then you plot the behavior on a piece of paper as it comes out of your printer, and then you take this piece of paper and you give it to Myra, and she passes it through a shredder. So what used to be a beautiful partial differential equation space-time field now becomes a string of 512 colored strings that are messed up. And if you just randomly plot them next to each other, you get this. You understand what this is? These are the 512 strings in random order. Well, if you think of each one of these strings as a data point, because the PDE is smooth, each one of these strings has one string that is closest to it, actually two strings that are closest to it, one on the left and one on the right, yes? But you don't even know who of the two is the left and who is the right. You're with me? This is exactly the same algorithms that you may have read. There is algorithms for solving puzzles. This is exactly what we did solving puzzles when we were kids, and for those of you that have kids and grandkids, this is what you do. You take the pieces, and then you see which piece is close to which piece, and then you put them together. This is based only on the colors. You know that in most of the puzzles, it's not just the colors, but it is also these little teeth that they have to help you, because the colors would be more difficult to figure out who is close to whom, right? So what you do is that you take all of these guys, and by just looking at who is close to whom, what you can do is that you can recover the right order. And as a matter of fact, if you are careful and look at it, you will realize that this and this are flipped, because when you find your neighbors, you don't know who is the right and who is the left neighbor. So what you get is the same thing modulo a flip or an orthogonal transform arrow in general. So what is it that I'm really telling you? What I'm telling you is you may have behavior that depends on space and time if you don't know about what is the right space, right? If you have thermocouples but you don't know where in the reactor the thermocouples are, then you can look at the behavior at that point, and you can use this to recover something that is one-to-one with the space. You're going to say, this is really weird. I mean, when is it that I'm not going to know what the space is? Usually I should know where I put my thermocouple. Well, let me kind of go a little further. This is the same idea, but now I am not just shredding a page, I'm shredding an entire book. So this is a two-dimensional partial differential equation, and this is time. You take this cube, and what you do is that you push it through one of these meat grinders, so you get like 200 by 200, you get 40,000 meat strings, and they're all mixed up, and you don't know how to put them together again. You look at each one of them as a data point. You look at smoothness. In particular, we did diffusion map on those. The algorithm comes back and tells you this is a two-parameter family of time series, and this is the right topology of who is close to whom. Now you realize this is not the original square, but I'm sure your eyes tell you they are one-to-one. And if you really look at it carefully, you will see that they are flipped. You see, this goes this way while the other goes that way. So you expect to get something that is one-to-one with the true physical space, but not necessarily exactly it. And as I said, how is it possible that you don't know what the space is? Well, I hope you will like this. I and Tom Bertel and my student who did this. This is what you see here is 1,024 oscillations. They are little closed curves, limit cycles. This is the behavior of a network of not all-to-all. It's a Chung-Lu network for those that care about it. It is a network of coupled oscillators. These oscillators are different from each other, and you see that each one of them is doing a different thing. Why are they different from each other? They're different from each other first because their intrinsic kinetic constants are different. And they're also different from each other because they are connected to each other in a different pattern each. So there is two kinds of heterogeneity in these oscillators. They're heterogeneous intrinsically and they're heterogeneous structurally. What we do is that we take these 1,024 closed loops and we do data mining on them. And what the data mining comes back and tells us is, you know, these 1,024 oscillators, they really are a two-parameter family of oscillators. And if we go and color this intrinsic data-driven representation by the heterogeneity in the kinetic constant, do you see that the phi1 variable discovered by the data is one-to-one with the kinetic heterogeneity? And here we color them by the degree distribution in the network, and you see that phi2, the second kinetic, the second data-driven parameter, seems to be pretty close to one-to-one with the structural heterogeneity. So what I am basically telling you is that if you don't know what the heterogeneities are, doing data mining on the behavior is going to tell you how many dimensions of heterogeneity there are, and it will give you a way to parameterize these. Where am I going with this? Here is where I'm going with this. Here you see the behavior of these oscillators plotted not by saying what oscillator number 1 does, what oscillator number 2 does, but by plotting the oscillators based on these data-driven coordinates. You see that the behavior of the network really is the discretization of a PDE in these two dimensions that parameterize the heterogeneity of the behavior. In the same way that in a two-dimensional flow, you have different velocity histories at every x and y, here in this large network, which is parameterized by 2 degrees of heterogeneity. At every different position, you get a different behavior, but nearby positions do nearby things. So what I am really telling you is, this is a problem that is not a partial differential equation. But if you analyze the data, you understand that you could model it as a partial differential equation, and the space variables for this partial differential equation are the heterogeneity parameters of how different the oscillators are. So this is, the funny physics word is, this is an emergent partial differential equation. It is something which, if you look at itself, it just is a network, a messy network. But if you look at it, you realize that it could be described as a partial differential equation in time and 2 variables, and these variables come from the data mining of the behavior itself. We don't have a blackboard, but let me try and tell you this in words. Think of having a 2-dimensional reaction diffusion equation, 2-dimensional in space, okay? Everybody knows if you do finite differences, you know that you're going to get banded matrices, yes, in the discretization. When do you get banded matrices? You get banded matrices if you order the nodes 1, 2, 3, 4, 5, 6, 20, 21, 23, 40, 41, 43, 60, yes? Suppose that you don't order the nodes like that. Suppose that you give all the nodes a random numbers from 1 to 10,000. If you plot it randomly, it will look like a random network. But if you look at what happens at every node, then you try to put together nodes that have similar dynamics, then you will recover something that is 1-to-1 with the original space. So you know there is this English expression, handsome is as handsome does. You don't look at who you are, you look at what you do. And then you create a space based on the types of behavior. If you want, how good a student you are depends on how much you're studying and how smart you are, not where, in which dorm you happen to live. Although maybe there is dorms for nerds. I don't know how to do from here. So why is this interesting or important? This is, if you want, the case in which not only the dependent variables, but maybe even the independent variables of a good realization of the model might be coming from data. And I said no time. Remember when I took this page, I shredded it lengthwise? Well, what if I rotate it and shred it sidewise? So then I am not taking time series at one point. I am taking snapshots in time. Well, if you take the snapshots in time and ask which snapshot is close to which snapshot, it's a good chance that it is going to give you something that is in the right order, right? So actually, when I first created this, there was a company in California, and now I don't think you need to pay anybody to do this for you, in which if you gave them, like, you know, suppose you went to your parents' house and you find an old drawer that is full of photographs, then you can give it to them and then they will put it in chronological order for you, because they're going to look at the faces of the people and then they're going to see how they age, and they are going to create the right chronological order. So this is, you take it, you mess up the times and you can recover it, and there's nothing special about cutting in space or in time. You can take a cookie cutter and cut little patches of space-time, and then you mix them all up, and this is now much more like a 2-dimensional puzzle. You can put them back together again. So this is kind of a little example of this. This is Germany. This work was done with German collaborators. What you see here is a map of Germany observed in the traditional way by walking from city to city. And then this is a map of Germany observed in a very strange way. You go on a given October day, I think it was late October of some year, at each one of the cities, and then for each one of them you create a Boolean vector that says for how many, up to what time you have night, and when does the sun come up, and then when does the sun come down. It's straightforward that when the sun comes up and when the sun comes down is very strongly correlated with what is your geographical location, latitude and longitude. If you take these vectors and you do data mining on these vectors, then you get something which is not exactly Germany, but you can clearly see with your eyes that is 1-to-1 with a map of Germany. So what I am basically telling you is that if you do not know the right independent variables, then it is possible, if you have enough information from the behavior, to create a good embedding space in which you can describe the thing as a partial differential equation. The reason why this is important brings me to what I kind of want to conclude with. This is a particular partial differential equation. It's called Kuramoto-Shiroshinsky. When I was young, I spent a lot of time on it. This is one space dimension and time, and what you see is a modulated traveling wave. I'm sure you can see that this is something that travels in space-time, but you see that it doesn't travel with constant speed. It has this slightly wavy motion. So this says that the attractor is a torus, a T2. What I basically have told you is that whether my observations come from sitting at one particular location and getting time series at that location, or whether I sit at different times and get little space snapshots at these, or whether I sit at some point in space-time and get little space-time patches around that point, or whether I may even have traveling observers as long as their trajectories don't intersect. It is possible to get all of these different observations and map them to each other. That is, it is possible to take different observations of the same phenomenon and register them. This, in my opinion, I've said it to a few of the people today, is one of the biggest things about data science. Normally, we try to make models in terms of quantities that we understand. If we all understand we use the same quantities, we're going to hopefully get the same model. Here, some of us is going to measure these 5 things from a model, and somebody else will measure from a system, the other will measure some other things, the third will measure some third things. Each one of us will make a model. The point is, can we understand that we are really observing the same thing? Can we create, in a data-driven way, a mapping between rich enough different observations of the same thing? I was telling Jeff that I had a friend who wrote in the financial world in the late 90s a paper called Reconcilable Differences. In it, there were 3 completely different sets of observations of the market. There were 3 completely different optimization functions, and all the buy and sell decisions from the 3 models were the same, which basically means that all 3 of them were rich enough observations of the same thing. Okay? So I want to give you a little explanation of how it might be possible to actually do something like that. If I have completely different observations of the same thing, how can I understand that they can be mapped to each other? How can I create a diffeomorphism, a mapping, a data-driven mapping that takes me from the one to the other? To do this, I have this slide. Let's see how well I can say this. Let's say that this is how I look at the problem. This is how one of you looks at the problem. And then this, I sometimes would say here, God space, but this would not be appropriate, especially maybe at Notre Dame, so I wrote Plato space. So you think of an idealized version of what the system is. There's one thing that I will ask you to believe. I apologize for this. When we do diffusion maps, it is very important that we don't work with the measurements themselves, but we work with differences between measurements. So we look at nearby realizations, and then we have some measure of how similar or different they are. We don't look at what they are themselves, but the differences between them. So let's say that in some sort of idealized space, this is the distance between 2 measurements. If my observation function in my space is the identity, then I see exactly the same distances that Plato sees, and therefore my data mining and Plato's data mining is going to be the same thing. But if this is my observation function, what is important for my observation function? It is monotonic. It is 1 to 1. It does not fold over Plato space. There's no different things in Plato space that look the same to me. What are different for Plato are also different for me. Okay? But you realize that this distance and this distance are not the same anymore. So if I do data mining in my world, I will see different parametrizations than Plato. Here is the fun part. If I don't only look at a single measurement, but if I look at a little cloud of measurements around here. So if I, let's say, have a little Gaussian sampling of measurements around here with variance 1, then because this is not the diagonal, what is going to happen is that what is a nice Gaussian with variance 1 here will have a different variance over here because of the slope of the observation curve. And if these points are not too far from each other, then by looking at what happens to a few nearby measurements, I can get the slope of the observation curve. And if I have the slope of the observation curve, I can use the distance and scale it by the slope of the observation curve and get a very good estimate of what Plato would have seen from the same data. So what's the secret? Don't just measure one measurement. Measure a little in the neighborhood of what it is that you're seeing. This will give you a way to transform into an idealized space. Let's say that you come in and you have a completely different observation curve, but is again monotonic. It's very important. It's 1 to 1. Then your distances are going to be very, very different. But again, if you take these measurements and you look at how the covariance of the local noise is transformed by the observation. So for those of you that play with this, there is a name of Mahalanobis that is infused, it is connected with looking at the local covariance of the noise, the local information matrix, and scale little local distances based on this. Then these distances scaled by these slopes and these distances scaled by these slopes can be mapped to the same Platonic distance. And if you look at this, you see this green and blue thing, I did it on purpose like that. You see that it looks like a lens? It is a way of creating observers from sufficient observations with one instrument and sufficient observations with the other instrument. So there exists, if you have the ability to measure little local clouds of measurements, there is a reasonable systematic way of doing your data mining in a gauge invariant way, in a way that does not depend on the measuring instrument, as long as you have rich enough information. And let me kind of, okay, so when I was at Princeton, the engineering school is very close to Princeton University Press, where they have a lot of very good graphic designers. So I went to a graphic designer and we talked for some time, and I tried to find an interpretation of what I just told you. So this is Newton, and this is your observation of Newton. You look at Newton's shadow, yes? And then here is something completely different that happens to have the same measurement, yes? What I really told you now is that if you don't just look at Newton with the light coming from this source, but if you jiggle a little bit the lights, then you're going to get a whole bunch of local different shadows of Newton. I know it's a funny little example, but I hope it conveys the idea. So by looking at nearby measurements, you get a quantitative measurement of context. And even though the measurements are the same, the context for Newton and the context for the vase are completely different. And so you can understand that these things are not the same thing, while if you measure Newton from this way and Newton from that way, you can understand that this is the same thing that you're measuring. And now, let me see, the time is over, and yeah, I have 2 minutes. Let me kind of go over this, and as I said, I promised that I promised Nick that there would be some degree of entertainment. So let's see how entertaining this is. Do we have sound? Okay, so this, I happen to like this. This is the fourth cembalo concerto of Bach, which actually happens to be, stop, which happens to be a translation of the four violin concerto of Vivaldi. I'm just trying to tell you that you are hearing the same music. You hear it in very different frequencies, but you understand that it is the same piece. So this idea of, if you think about it, what is the heart of this? We're talking about translation. We're talking about different representations of the same thing, and it happens in music. This is also working with this guy at Princeton University Press. So, you know, in the Middle Ages, in the Renaissance, in painting, people tried extremely hard to paint exactly what they saw, okay? So in the early Renaissance, this again, I think this is Plato and this is Socrates, this is the Academy of Athens. You know, they discover perspective, there is the point at infinity, everything looks like the projective plane. There is a lot of work that goes into painting exactly what you see. This is a Dürer print, you see how much trouble they did in order to kind of paint exactly the correct perspective and what they saw. And then what happens is that photography comes along, and all of this is useless, right? So what people try to paint is what they feel when they see something. So this is the Cathédrale de Rouen, I think. These are different views of the same thing, and you're supposed to kind of think of, and if you think of this is a woman, if you think about it, viewed by two cameras, because you can see both this side of the eye and the other side. And you know that the Egyptians also did this. They deformed the object for better explanation value, okay? And we Greeks also stole it from them. So this is, you see, the eyes are wrong. The faces are fine, but the eyes are wrong. And then people try to paint, so this is nude going down the staircase. You try to paint a movie. So you try to have a whole time series in your data. And then you all know this maybe, where people used, come on. For some reason it does not work. You can use still pictures of a horse to make a movie of the horse running, and the point was to show that at some point all legs of the horse are off the ground. This is Muybridge. And if you think of what we do today, is that we actually have several cameras to look at the same object, in part because we want to be able to see everything that happens even if we're not looking directly at it, but we also have ways where we show the object and we show what you should observe from the object. I know that today it is possible to, people are working on how many cameras should you have so that you could record a Broadway play and then you could walk through the Broadway play yourself, in a sense. So this idea of being able to map different things to each other is something that is more and more and more important. When can you calibrate one model to something else? I've run over for 2 minutes. I will ask you can leave. I can ask your indulgence for 2 more. This is Jhumpa Lahiri, who has a Pulitzer Prize in literature, and who also, at some point in her life, decided to start writing in Italian. So she wrote a book that's called In Other Words. So this is, if you want, this is the most fundamental version of gauge invariance. Translation, different languages. How do you say the same thing in different languages? So she writes this book, and one page is in Italian, hers, and the other page is the translation of the Italian by somebody else. And I read this book, and it is a beautiful book. Everything is, the words are beautifully sculptured and chosen. It is really, in some sense, a literary gem. But in some sense, to me, we should not be recording, it gets to be monotonous, because it basically says how difficult it is to give idioms of one language into expression in the other language. How difficult it is to freely speak in 2 languages, translate one language to the other. And so I'm going to put the book down after the first 30, 40 pages, but then I say, let's see, is there anything interesting at the end? So I turn, and there is this afterword, and the afterword floors me. So I will read you just 2 paragraphs from her afterword, the translation. Look, in 1939, 15 years before he died, Henri Matisse began to move away from traditional painting and develop a new artistic technique. It involved cutting up pieces of paper that had been painted in gouache in various colors. Matisse then combined and arranged the different pieces to create an image. He fixed the elements first with pins, then with paste, often directly on the wall. He stopped using the easel or the canvas. His main tool became a pair of scissors rather than the brush. You think of this, they're talking about pixels of color. He cut pixels of color and put pixels of color on the wall. It's interesting to look even a little further. The method, a sort of synthesis of collage and mosaic, had some limitations. He couldn't paint very well, he was old, So you don't do it for better, you do it because maybe you cannot do the other thing, okay? This is the best you can do. Let me just say one last thing. For Matisse, the second one, the images on paper were more simplified, crude compared to the ones on canvas, but they required painstaking, complex workmanship. Nobody said that data mining is easy. There is a lot of science and work that goes in there. One recognizes the hand and the eye of the painter, but they have changed. We follow the thread between the new method and the earlier paintings, and we are aware of a turning point, a radical move. Last thing I'm reading to you. For Matisse, cutting was not only a new technique, but a system of thinking about and expanding the possibilities of shape, color, and composition. In some naive way, I'm trying to tell you that the machine learning assisted or data science assisted modeling is a system for thinking about and expanding the possibilities of analytical closed form modeling that we know how to do. A rethinking of his artistic strategy. The painter said the conditions of this journey are 100% different. He compared his method, which he called painting with scissors, to the experience of flying. And basically I'm stopping, and what I wanted to say is that this is maybe one of the things that I wanted to say, that the ability to work with many different transformations of different data coming from the same problem allows you to rethink the way that you model and not work only with being able to build in mechanistic understanding, but being able to build a lot of new capabilities. I sound like I'm selling used cars. It's a fun thing to do, and it's a good time to be alive and work at modeling. Thank you. Sorry for running so much over.
We have time for any questions?
Yes.
Really nice talk. So when you're doing the paper shredding, or maybe the cross-cut shredding,
yes,
when you're doing both ways, is there a fundamental limit to how finely you can shred?
To how finely you can shred, no, but you have a point. The reason that this thing is working is because there is no recurrences. There is no points further down at which you get exactly the same thing, or something that is so close exactly that things would. So it is very important that one-to-oneness is very important. And I had asked you to ask me, let me maybe say this. Remember that I said something about explainability. As a matter of fact, I've heard, I don't know if it is true, that in the European community, in the European Union, it is supposed to be that since last year, every decision that is based on a machine learning algorithm is supposed to only be implementable if there is a human explanation. I don't know if they are applying this and what the lawyers have to do. But what I wanted to tell you is the following. The most important in everything that I've told you is that the machine coordinates and the human coordinates, it is very important that they are one-to-one with each other. How do you check if two things are one-to-one with each other? You look at the Jacobian and make sure that the Jacobian never becomes singular. So, if the computer tells you, here is the variable phi1, phi2, and your knowledgeable chemistry friend tells you, you know, Yannis, I think the concentration of this radical and oxygen are important things to know. You can look on your data at the Jacobian oxygen radical to phi1, phi2. As long as this is by Lipschitz, nice, as long as the slope is neither infinite nor zero. You understand? If you have a variable and another variable and the slope is zero, this variable changes and the other doesn't change. They are not good measures of each other. If the slope is infinite, this variable is not changing and the other one changes. They're not good. As long as the slope lives in a wedge around the diagonal, which you can test numerically, then the information in these two from the computer and the information in these two that was given to you by your friend encode the same manifold, parameterize the same manifold. So A, you can test if this is explainable. If somebody gives you some suggestions, you can check if this suggestion or that suggestion is one-to-one with what you found. Second and last, please notice, it's not as if there is only two physical things that will be one-to-one with the two that you found from the computer. Think of just this, think of a little part of a surface this little part of the surface that I am kind of trying to draw with my hands is one-to-one with x and y on the floor, but the way that I drew it is also one-to-one with x and z on the wall. Do you kind of see what I'm trying? So there may be many different, equally expressive sets of physical variables that could give a result. And last things for the chemical engineers, I think I used this example today. Think of an adiabatic process. If you think an adiabatic process, all the